All right, we're going to get started. We're going to continue where we left off yesterday. So yesterday we were talking about xenon, and we wanted to do the noble gas shorthand. And, oh, I don't know, you can't probably see that on my screen, but looking at xenon, it is right here. Oh, it's blocked. Well, let's just do it this way. All right. Right there is xenon, and we want to figure out the noble gas shorthand because nobody wants to start at hydrogen, do 1s2, 2s2, 2p6, 3s, all that. No. So we're going to do noble gas, and the noble gas that comes before it is the one that we write down. You can't just put xenon in brackets because that looks like concentration of xenon. It's not what we're talking about. So we got to do the noble gas that comes before it, which is krypton. So, wait. We weren't doing xenon. We were doing radon yesterday. Is that right? Yeah. Okay. So let's just bump it down one. So if we're starting at radon, we want to start with xenon. If you want to figure out radon. So we put ZE in brackets. And then we continue on from xenon number 54 to 55. 55 is in column 1. It's in the S section, but we're in 1, 2, 3, 4, 5, 6. Row 6, so energy level 6, n equals 6, further from the nucleus. So I'm going to write 6. It's in the S section. And remember, the S orbital can only have how many electrons? 2, max of 2. So 1, 2, and I filled it up. That's as far as I go. But then I continue on to the, we didn't really talk about this yesterday a whole lot. It's S, P, and then this is the D. D as in dog, the D orbital. And that's the 5 different suborbitals, each with 2 electrons, max of 10 total for the D orbital. And it's in the 6th row, but the D's are always going to be one less than the row they're in. So we're going to call it 5D. Why is it less than one less than the row it's in? Is because there are 10 electrons, so there's a greater electrostatic attraction between that orbital, that negatively charged orbital, and the positively charged nucleus. So it kind of comes closer to the nucleus, normally than we would expect. Or you just think it's one less than the row it's in. But, if we go to the F orbital, we're going to see how it's even lower because there's even more electrons. So it goes down a little bit more. All right, so we got, where are we? Right here. 1. Hey, notice how it goes from 57 to 72. That's crazy because 57 scooched down to number 58. This is called the inner transition metals because it's in between inside the row that has the transition metals. And normally if we were starting at like samarium or we're trying to figure out curium, we would have to do 5D1 and then continue on to this. And even though this is in the 6th row, it's 2 less than the row it's in. So we would call it not 6F, because these 2 bottoms are the F orbitals, but we would call it 4F. So this is the 4F, this would be the 5F. We don't have a 6F because there's not enough elements discovered yet. I guess you could have one if it's excited. It would go into that theoretical outer 6F orbital. But the thing about this is radon, we're looking at 86. If you scooch all the way to 71, do we include all these? Yes. Do we include all of these? Yes. So it's a moot point. We'll do like uranium as an example so you can see what we're talking about. So you're going to have the 1 in the D, and you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 in the F. And then you're going to continue in the D. So you would just lump it all together, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we stop right there. Because then this goes into the P. Alright, so that makes sense. And then we got to include the F ones in there. So that was 4F. 1, 2, 3, yeah, 14. 4F, 14. And then that brings us from 71 to 72 all the way to number 81 we're at. Now we're back. We're still in the 6th row. P orbital only has a max of 6 electrons. There's not enough electrons to bring it closer, so it's going to stay in that 6th energy level. So you're going to call it 6P. 1, 2, 3, 4, 5, 6. And we got it. So that's as hard as it gets. That's the tough one. Kind of went right to the tough ones. Speaking of tough, why don't we do uranium? All right. So uranium is number 92. If you get any bigger in uranium, you get into those ones that nobody knows about because they last for less than a second. So uranium is number 92. Which one comes before 92? Radon. All right, that makes it a little bit simpler because we're starting at 86. So we got radon. Radon's 86. Number 87 is right here. That's in which row? 7th row. You got it. 7th row. Which letter would it be? S. And we're going to fill it up. 7s2. 1, 2. But now we're at 89. It's in the D section. But what do we call it? Not the 7th row, but the 6th row. So it's going to be 6D. And there's only one. 89, because after 89 comes 90. And you go into the F. So we're going to call that 6D1. And then we're going to move on to the F orbital. And this is, what are we going to call this? This is what F? Oops, sorry, 5F. So it's in the 7th row, but F is going to be 2 less than rows in, so we call it 5F. And then we count 1, 2, 3. There we go. And that's the electron configuration for uranium. So if you get doing the noble gas notation, it makes it way simpler. Way simpler. Be careful. I just want to double check the periodic table configuration because they put La and AC right in the D, which is where it is electron-wise. However, you could see a periodic table like this, where they lump, sorry, it's cardstock, La and AC right here, which is true, but it's inconvenient for looking at electron configuration because now you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That could throw people off. And I just want to double check on. So what I want to do is orbital filling diagram. We talked a little bit about it yesterday. S is 1 circle, P is 3 circles, D is 5, and F is a lot of circles, 7. Since we already have the electron configuration written out for these, why don't we just do these? And you can do it shorthand. You could write all of them out. Just for the sake of time, let's just do it the noble gas shorthand. So I'm going to write neon. And then S has 1 circle. And there's 1 electron. So I'm going to do an up arrow. And I just do like a half an arrow that's going up. And there it is. That's the orbital filling diagram. But what if you're doing radon? So we got to put xenon in brackets. And I probably don't have enough room. Nope, I'm pretty sure I don't have enough room. So I'm just going to rewrite it over here before I get crowded. All right. So then I got 6s. So that's 1 circle. And there's 2 electrons in it. So I'm going to do 1 up, 1 down. That's the Pauli exclusion principle. You can only have max 2 electrons, both going opposite ways. And then we've got D has how many circles? 5 circles. And we got to follow Hund's rule. We got to fill in each circle with 1 electron before you can pair them up. In this case, it's a moot point because they're all going to be paired up. So that's Hund's rule. Got to fill in each suborbital with 1 electron before they can pair up, because that's lowest energy. Then we got 4F14, that's 7. 1, 2, 3, 4, 5, 6, 7. That's a lot of, here, let me do it right. Let's fill in each one. There we go. And then we've got, oh, this one's, sorry, P has 3 circles. This is an inconvenient example because it doesn't show you Hund's rule. Because again, we got to fill it all the way up. 1, 2, 3, 4, 5, 6. All right, so that's radon. Doing uranium, I think yeah, let's squeeze it in right here. We got radon, 7s2, S is 1 circle. There's 2 electrons. D is how many circles? 5 circles. And there's just 1 electron there. Fill in the first one. And should I squeeze this one in? Yeah, let's try it. 1, 2, 3, 4, 5, 6, 7. Here's a nice example of Hund's rule. I got to fill each one up with 1 electron before I can pair them up. So 1, 2, 3. And that's the orbital filling diagram. In the IB, they're circles. If you're taking AP, it's squares. I like squares better, but oh well. Questions so far? Does this kind of ring a bell from sophomore year?
Yeah, a little bit.
A little bit.
Why do you put P at the end again?
So the order is, wait, for this one?
Or, no, for the one very top.
Oh, which one was this? Oh, 6p6.
Yeah, very long.
So which one was that? Radon? So radon ends at 1, 2, 3, 4, 5, 6 in the P section. So this is all P.
Mm-hmm. So you put that at the end?
You put it at the end, yep. Because those are the last electrons that are added, so they're kind of the highest energy.
Gotcha, thank you.
All right, so that's the simple part. Now we're going to do all the weird exceptions that IB wants you to know. And IB really likes to talk about the first row of D elements. Those are all the exceptions. Why do they do that? Because if you go down to the next row, there's different exceptions. And it's too much to try to remember, so they're just focusing on the first row. So, am I talking ahead of myself here when electrons? Oh, yeah. So we'll come back to what I was just talking about when we talk about crazy chromium and curious copper. But first it says when electrons are taken away or added to an atom, they're taken away from the orbital that's farthest from the nucleus, not necessarily the orbital that has highest energy. So this is talking about how do you do electron configuration for an ion, something that's positively or negatively charged, something that has more than the normal amount of electrons or less than the normal amount. So why don't we let's do calcium 2+. Start with a simple one. Calcium is number 20 on the periodic table, so let's just shorthand it up. Well, here, I'll just write it out so you can see what's going on. So we got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that's normal calcium. But we want to talk about calcium 2+. So 2 electrons are lost. Which ones are going to be taken? The valence ones or the outermost electrons? We got first energy, second energy, third energy, and fourth energy level. If you're doing the Bohr model, we got 1, 2, 3, 4. Fourth energy level has a total of 2 electrons that are going to be taken away. How many electrons are in the third energy level? 8. 6 plus 2 is 8, so there's a total of 8 in the third energy level. You guys remember the Octet Rule? Oh, the Octet Rule is just the rule of thumb that elements want to have an overall 8 outer electrons. So if we take away these 2 electrons, the outermost valence is the third energy level, which has 8, and that's a very stable configuration. So that's why calcium always wants to get rid of 2 electrons to become more stable, because then its outer valence has 8 electrons. So technically, I would write this as 1s2, 2s2, 2p6, 3s2, 3p6. If you wanted to, you could write 4s0. But you don't need to. So that would, this is not calcium 2+, the bottom one is. That's fairly simple, but what happens when you're doing something like iron, get it right, let's do iron 3+. So iron 3+, and let's just go through the whole thing. 1s2, 2s2, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. Alright, so that's regular iron. But we're getting rid of 3 electrons, so I'm just going to pull them from this 3d and call it 3d3 and be done. Can't do that because what energy level is 3d in? The 3rd energy level. Is the 4th energy level further away? Yes. So you got to pull the 4s electrons out first, and then if you still need to pull more out, then you take them from the d. So that's kind of tricky. 1s2, 2s2. Oh my gosh, I forgot something here. 2p6. Sorry about that. Let's do 2s2. 2p6. If you want to write 4s0, you can. I'll just write 4s0. Or you can omit it and just have the last one be 3d5. Alright. Let's do the other way around. Let's do like S-. So normally fluorine is 1s2, 2s2, 2p, 1, 2, 3, 4, 5. But if it's -1, then we're adding an additional. So instead of 2p5, it's 2p6. So the only difference is now we're adding electrons if it's a negatively charged ion. Questions on that? You guys ready for the exceptions?
Oh, thank you.
There's only 2 of them. There's cray chrome and curious copper. Thing about chromium, it's right here. But let's just write out what we think chromium would be. So, oh, they even give you a hint there. But since 4s and 3d orbitals are almost equal, yeah, well, that'll make sense after we do it. So, yeah, why don't we do shorthand notation should work for this. So argon. Got argon. We're going to 4s2. And then 1, 2, 3, 4. Alright, so this is what chromium should be. I'm going to do the orbital filling diagram. Alright, so that's how it should be. However, there's a little rule, and something that is lower energy is when you are half full. So half full, meaning you could add twice as many electrons potentially, is going to be lower energy and more favorable. So this would be an excited state for chromium. So what we got to do is this 4s electron is going to skedaddle over to the 3d4 and make it 3d5 half-filled. That way you have 2 half-filled orbitals. This is only unique for chromium because of the amount of electrons it has. So we would write it as argon, 1 in the s, and 1 in each of the d orbitals. So if we write it out, it would be 4s1, 3d5. So chromium is one that you're going to want to remember, look out for. It's an exception. And the rule of thumb is it's lower energy to have half-filled orbitals if it's a possibility. So do you think the similar thing happens with curious copper? Probably. Well, yeah, probably not would be a good hypothesis. So copper, we're going to start with argon. 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. Okay. 4s2 3d. Oh, hey, look at, well, let's write the orbital filling diagram for this. So we got that, 2, 3, 4, 5. All right, so they're all filled except for the last one. This is a higher energy state than if you had something that was half full and completely full. So in this case, the 4s could be half full by moving one of the electrons to the d to make it totally full. That's going to be a lower energy configuration. Curious copper. So you're not adding or taking away any electrons, you're just shifting them over so that you have orbitals that are half full. All right. That's pretty much electron configuration orbital filling diagram. Fairly straightforward, it's just getting the pattern down. And then there's one more thing, quantum numbers, we're going to quick talk about. IB's not really too focused on quantum numbers on the zoomed-all reading. This is the bonus. You just got to email me those bonus questions if you want bonus points for that. You guys ready? All right, this is the last bit. AP really likes quantum numbers, so if you took AP, you'd be focusing on this more. But just in case, you're probably going to see chemistry in college, so you'll probably see that this is typically found in your Gen Chem course. You got quantum numbers N. I already mentioned that. That's the energy level, how far from the nucleus it is. That's what that says. And the bigger the number of N, the further from the nucleus. Then you got angular quantum number, which is represented by L. And L is basically talking about in the orbital, where is it? If you're talking about P with 3 circles, is it the first circle, the second circle, or the third? Which suborbital are we talking about? And they're given as integer values. So S, do we have this? Yeah, if you're doing like S, it's written as 0. If you're doing P, it's -1, 0, 1. If you're doing D, it's going to be -2, -1, 0, 1, 2. Notice how I have a 1 circle for S, 1, 2, 3 circles for boxes, for P, and for D I've got 1, 2, 3, 4, 5. So what do you think F would be?
7.
It would be 7, and I would start at -3. Go to 0, 1, 2, and then 3. So that's where that's coming from. Yeah, we fill this in. We've got S, number of orbitals is 1, and then we've got 2 electrons. Here, let's talk about these first. So magnetic quantum number M Sorry, so all of this stuff that we were talking about, this is our L. So for this one, for some space, S equals 0, P equals 1, D equals 2, and F equals 3. That's what this is talking about. So you got all these different numbers that are kind of similar. So N is how far from the nucleus. L is going to be 0, 1, 2, or 3, and that's what's the shape of it. And then M is going to be, is it 0, that's S, Is it -1, 0, 1? Is it -2, -1, 0, 1, 2? Which circle are you talking about? Or suborbital? All right, and then magnetic spin, it's either +½ or -½. That's up arrow, down arrow, essentially. It's going clockwise or counterclockwise. All right, to fill in this chart here, it might be helpful to use a periodic table. Quantum number 1 relates to the first row, and in the first row you just have one S. You don't have one P, no such thing. So you can only have S. But in the second row you can have 2S and you can have 2P. So you got S and P. Can you have 2D? No, it doesn't exist. 2D does not exist. Number of orbitals, S can only have one suborbital and P can have 3. And then total number of electrons, S can have 2 and P can have 6, so that's a total of 8. So 2 and 6 is 8. All right, so then the third, you can have S, you can have P, and then the fourth row of D's are called 3D. So you can have S, P, and D. Number of orbitals for S is 1, P is 3, and D is 5. And you can have a max of 2, 6, and then the D can have a max of 10. All right, 4. Can you have an F in the fourth energy level? Yes. So it's in the 6th row, but we call it 4F. So you can have all of those. We got 1, 3, 5, and 7 for F, each with a total of 2 electrons, 6 electrons, 10, and potentially 14. All right, 5. You could have S, P, D, and F. Looking at the pattern, do you think you could have G? You could have G, and G would only exist if the electron's in an excited state, because we don't have enough elements discovered to determine G. How many orbitals do you think G would have? Let's just put G.
9.
It would have 9, you got it. And then you're correct, 18 electrons. I'm just putting it down there to show that those would be in an excited state or theoretical. All right, you're not going to see that on the test. You're not going to see it in the IB exam in May, those things. But you may see it next year in college. All right, that is that.